everything you have ever known, every person you have loved, every dream you have dreamed, every civilization that has risen and fallen across human history, all of it exists within a single spiral arm of one galaxy, among hundreds of billions scattered across an ocean of darkness so vast that light itself becomes a pilgrim, wandering for eons between distant shores. Tonight, we will journey beyond the comfortable boundaries of our world and witness something that few minds dare to truly contemplate: the actual scale of our Milky Way within the tapestry of existence itself. Imagine, for a moment, that you could rise above your current position, through the ceiling, past the atmosphere, beyond the orbit of the moon. Keep rising. Watch as Earth becomes a marble, then a pixel, then vanishes entirely into the scattered light of the inner solar system. The sun, our constant companion, shrinks to a single point among countless others. Still you rise, passing Neptune, crossing the heliopause where solar wind gives way to interstellar space. And here, billions of miles from home, you have barely left the doorstep of our cosmic address. The stars that seemed so distant from Earth now reveal themselves as neighbours, clustered in a great spiral structure rotating through the void. This is the Milky Way, our island universe, home to somewhere between 100 and 400 billion stars, each potentially hosting worlds of their own. We live approximately 26,000 light-years from its centre, tucked into a minor spiral arm called the Orion Spur, orbiting the galactic core at over 500,000 miles per hour, yet taking 230 million years to complete a single revolution. Everything humanity has ever accomplished has occurred in less than one galactic rotation. But even this is only the beginning. The Milky Way itself is not alone. It drifts through space as part of a gravitationally bound collection of galaxies, which in turn belongs to larger structures, superclusters separated by cosmic voids, so enormous that galaxies themselves become merely grains of sand scattered across an infinite beach. To understand our place in this architecture is to undergo a fundamental shift in perspective, one that renders human concerns simultaneously insignificant and impossibly precious. This journey is designed to guide you gently through these scales, from the familiar warmth of Earth to the cold mathematics of cosmic structure. Whether you are listening as you drift towards sleep, seeking relaxation after a long day, or simply hungry for perspective that transcends the everyday, let this be a space where wonder and rest coexist. The narration will move slowly, deliberately, allowing each concept to settle like sediment through water, building understanding layer by patient layer. We will not rush. The universe has waited 13.8 billion years to be witnessed. It can wait a little longer while we truly see it. Before we begin our ascent, I would love to know, where are you right now? What corner of this pale blue dot are you watching from, and what time has brought you here? Leave a comment below. There is something quietly beautiful about knowing that across time zones and continents, people are sharing this same moment of cosmic contemplation, all of us passengers on the same spinning world, looking outward together into the infinite dark. Now settle in. Adjust your position. Let comfort find you. We're about to embark on the most humbling voyage possible, one that requires no spacecraft, no fuel, only imagination, and the willingness to see beyond everything you thought you knew about size, distance, and home. Let us begin at the only place we can, here on Earth, looking up. Before we can grasp where the Milky Way sits within the vast cosmic tapestry, we must first understand what it truly is. Not as an abstract blur in the night sky, but as a structure with dimensions, architecture, and rhythms that have unfolded across billions of years. Our galaxy is not simply a collection of stars. It is a living, breathing system, bound by gravity, shaped by time, and inhabited by worlds we will never see. The Milky Way is a barred, spiral galaxy, one of countless such formations scattered throughout the universe. Yet it is our home, and that makes it singular. Within its elegant spiraling arms lie between 200 and 400 billion stars, each one a sun in its own right, many accompanied by planets, moons, and perhaps even life. These stars are not scattered randomly across space. They are organized into a magnificent structure, a cosmic architecture that reveals itself only when we step back and observe from vast distances no human has ever traveled and perhaps never will. At the center of the Milky Way lies a dense spherical region known as the galactic bulge. Here, ancient stars crowd together, packed so tightly that if Earth orbited one of these central suns, the night sky would blaze with thousands of stars brighter than Venus. The bulge glows with a warm golden light, the accumulated radiance of billions of aging stars. This is the heart of our galaxy, a region dominated not just by stars, but by something far more mysterious and profound. At the very core, hidden behind veils of dust and gas, resides Sagittarius A, a supermassive black hole with a mass equivalent to 4 million suns. It does not shine, it does not roar, yet its presence warps the fabric of space-time itself, pulling stars into tight orbits that complete their circuits in mere years, speeds so extreme they challenge our comprehension of gravity and motion. Sagittarius A is not a destroyer, but an anchor, holding the galaxy together with invisible threads of gravitational force. Around this silent titan, the entire Milky Way revolves, a cosmic wheel spinning through eternity. Extending outward from the bulge is the galactic disk, a flattened spiral structure stretching approximately 100,000 light-years from edge to edge. This is where the beauty of the Milky Way truly reveals itself. The disk is divided into several major spiral arms, vast curving streams of stars, gas, and dust that wind outward from the central bar like water spiraling down a cosmic drain. These arms are not solid structures. They are density waves, regions where material congregates temporarily before drifting apart again, a pattern that persists even as individual stars move through it. The spiral arms have names that echo mythology and science: the Perseus arm, the Scutum Centaurus arm, the Norma arm. Each one glows with the light of newborn stars, massive blue giants that live fast and die young, illuminating the surrounding nebulae with brilliant ultraviolet radiation. It is within these arms that star formation occurs most vigorously, where clouds of hydrogen collapse under their own gravity, igniting fusion reactions that will burn for millions or billions of years. Our Sun does not reside in one of these major arms. Instead, it occupies a smaller offshoot known as the Orion arm, or sometimes the Orion spur. This modest branch extends between the larger Perseus and Sagittarius arms, a quiet stellar backwater approximately 10,000 light-years in length. Here, 26,000 light-years from the galactic center, our solar system makes its slow, patient journey around the galaxy. We are neither at the edge nor at the heart. We are somewhere in between, inhabitants of a galactic suburb far from the crowded chaos of the core and the lonely darkness of the outer rim. The disk itself, though vast in diameter, is remarkably thin. If the Milky Way were scaled down to the thickness of a sheet of paper, it would stretch for hundreds of feet across. This thinness is maintained by the rotation of the galaxy. Just as a spinning pizza dough flattens into a disk, the centrifugal force of the galaxy's rotation keeps most of its mass confined to a plane only about 1,000 light-years thick. Yet even within this narrow band there is structure. Young stars and gas clouds cluster tightly near the midplane, while older stars drift above and below, forming a diffuse layer known as the thick disk. Surrounding the entire visible galaxy is the galactic halo, a vast spherical region that extends perhaps 200,000 light-years or more from the centre. The halo contains very little visible matter compared to the disk, only ancient stars grouped into globular clusters and solitary wanderers that orbit the galaxy on long, eccentric paths. These halo stars are among the oldest objects in the universe, formed in the galaxy's infancy more than 13 billion years ago. They are the elders of our cosmic community, carrying within them traces of the primordial elements forged in the Big Bang. But the visible halo is only part of the story. Extending far beyond the light of stars is an invisible structure composed of dark matter, a mysterious substance that neither emits nor absorbs light. This dark matter halo is enormous, perhaps 10 times larger than the visible galaxy itself, creating a gravitational cocoon that holds the Milky Way together. Without it, the stars would fly apart, scattered into the void by their own orbital velocities. Dark matter does not glow, does not radiate, and cannot be observed directly. Yet its presence is undeniable, written to the rotation curves of the galaxy and the motions of its stars. To comprehend the Milky Way's structure is to confront the immensity of time as well as space. Our Sun, along with the planets, asteroids, and comets that accompany it, orbits the galactic centre once every 230 million years. This is known as a galactic year, or a cosmic year. Since the Sun's formation 4.6 billion years ago, it has completed only about 20 such orbits. When the solar system last occupied this exact position in the galaxy, dinosaurs walked the Earth. The time before that, complex multicellular life had not yet emerged. Our entire human history, from the first civilizations to the present day, represents less than 1/50th of a single galactic orbit. The concept staggers the imagination. While we measure our lives in decades and our civilizations in centuries, the galaxy measures its existence in rotations that span hundreds of millions of years. We are not merely small in space, we are small in time, fleeting inhabitants of a universe that turns at rhythms far slower and grander than anything we can directly experience. Even our immediate stellar neighbourhood operates on scales difficult to grasp. The nearest star to our Sun is Proxima Centauri, located 4.24 light-years away. Light, travelling at 186,000 miles per second, takes more than 4 years to cross that distance. With current technology, a spacecraft would require tens of thousands of years to make the journey. And Proxima Centauri is our closest neighbour. Most stars in our local region are separated by distances 5, 10, or 20 times greater. We live in what astronomers call the local bubble, a region of low-density gas approximately 1,000 light-years across, carved out by ancient supernova explosions that swept away much of the interstellar medium. This bubble is our backyard, and yet it is vast beyond comprehension. The Milky Way is not static. It breathes with the motion of stars, pulsates with waves of star formation, and interacts with neighbouring galaxies through gravitational tides. Small satellite galaxies orbit the Milky Way like moons around a planet, slowly being torn apart and absorbed into the larger structure. The largest of these, the Large and Small Magellanic Clouds, are visible from the southern hemisphere as fuzzy patches of light. They are being cannibalized by our galaxy, their stars stripped away over eons, adding to the Milky Way's ever-growing mass. Understanding our galaxy's structure is not just an academic exercise. It is a journey into the architecture of existence itself. The Milky Way is a machine of cosmic proportions, converting gas into stars, stars into heavy elements, and heavy elements into planets and life. Every atom in your body was forged in the heart of a star that lived and died somewhere in this galaxy, then scattered its enriched ashes into space, where they eventually coalesced into the Sun and Earth. We are not merely observers of the Milky Way, we are products of it, assembled from its ancient dust, animated by its energy and bound to its destiny. As we absorb the scale of our galactic home, from the silent black hole at its core to the dark matter halo that cradles it in invisible embrace, we begin to see ourselves differently. The Milky Way is not just a backdrop for human stories. It is the stage, the context, and the creator. Its structure defines our place, its history shapes our existence, and its vastness reminds us that we are part of something far greater than ourselves. And yet, as vast as the Milky Way is, with its hundreds of billions of stars and its 100,000 light-year span, it is only the beginning. For our galaxy does not drift alone through the cosmic void. It is part of a neighborhood, a gravitational family of galaxies that cluster together in the darkness. To understand the Milky Way's true position in the universe, we must now zoom out, leaving behind our spiral home and venturing into the space between galaxies where an even larger structure awaits. We have journeyed outward from Earth, across the solar system, past planets and storms and rings of ice, but now we must shift our perspective entirely. What if the Milky Way itself is not alone? What if our entire galaxy, with its hundreds of billions of stars, is just one member of a cosmic neighborhood, a gravitational gathering of galaxies bound together across impossible distances? As we pull back our view, the Milky Way begins to shrink. The familiar spiral arms compress into a luminous disk, and there, suspended in the darkness around it, other galaxies emerge, some large, some small, some brilliant, some faint. Together they form what astronomers call the local group, a collection of more than 80 galaxies held together by the invisible threads of gravity, across a region spanning roughly 10 million light-years. This is no longer a journey of miles or even astronomical units. This is a journey measured in millions of light-years, where a single light-year is nearly 6 trillion miles. At this scale, planets disappear. Stars become dust. Even entire solar systems fade into insignificance. What matters now are galaxies, islands of billions of stars, each one a cosmos unto itself. The local group is our immediate cosmic neighborhood, the gravitational family to which the Milky Way belongs, and like any family, it is filled with personalities, histories, and an uncertain future. The most striking member of the local group and the Milky Way's closest large companion is the Andromeda Galaxy. At 2.5 million light-years away, Andromeda dominates the night sky for anyone who knows where to look. To the naked eye, it appears as a faint smudge of light, barely visible against the stars, but through a telescope or from the vantage point of deep space, Andromeda reveals itself as a magnificent spiral, larger and more massive than our own galaxy. It contains over 1 trillion stars, nearly double the number in the Milky Way. Its spiral arms stretch across 220,000 light-years, making it the largest galaxy in the local group. Andromeda is not simply sitting in space. It is moving, and it is moving toward us. Every second, Andromeda hurtles closer to the Milky Way at a speed of roughly 250,000 miles per hour. This is not an approach born of chance. It is the inevitable pull of gravity, a cosmic attraction that has been building for billions of years. Andromeda and the Milky Way are locked in a gravitational dance, and their orbits are spiraling inward. In approximately 4.5 billion years, these two galaxies will collide. But this is not a collision like cars meeting on a highway. Galaxies are mostly empty space. The distances between stars are so vast that when Andromeda and the Milky Way merge, very few stars will actually collide. Instead, the galaxies will pass through each other, their structures distorting under immense tidal forces. Stars will be flung into new orbits. Gas clouds will compress, triggering bursts of star formation so intense they will light up the sky with millions of new suns. The supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging into a single, even more massive singularity. Over billions of years, the two galaxies will settle into a new form, likely an elliptical galaxy, no longer a graceful spiral, but a glowing sphere of stars arranged in a chaotic harmony. Astronomers have named this future galaxy Milky Way. It is a creation not of destruction, but of transformation. A reminder that even galaxies evolve, merge, and become something new. From a distant vantage point, billions of years from now, an observer might look back at this region of space and see not two galaxies, but one, blazing with the light of trillions of stars born from the union of ancient cosmic neighbours. Yet Andromeda is not the only galaxy in the local group. There is also the Triangulum galaxy, the third largest member, lying roughly 3 million light-years from Earth. Triangulum is smaller than both the Milky Way and Andromeda, containing only about 40 billion stars, but it is a vibrant galaxy, rich with regions of active star formation. Its spiral arms glow with young blue stars, clusters that have formed within the last few million years, a blink of an eye in cosmic time. Some astronomers believe that Triangulum is gravitationally bound to Andromeda, possibly orbiting it like a satellite. Others suggest it may eventually join the collision between Andromeda and the Milky Way, adding yet another layer of complexity to the future merger. Beyond these giants, the local group is populated by dozens of smaller galaxies known as dwarf galaxies. These are not the grand spirals or massive ellipticals that capture our imagination. They are faint, irregular, often containing only a few million stars. But they're no less important. Dwarf galaxies are the building blocks of larger galaxies, remnants of the early universe, and windows into the processes that shaped galactic evolution. Many of them orbit the Milky Way like moons around a planet, held in place by gravity, slowly being consumed by the larger galaxy over time. Two of the most famous dwarf galaxies are the Large and Small Magellanic Clouds. Visible from the southern hemisphere, they appear as fuzzy patches of light, companions to the Milky Way that have been known to astronomers for centuries. The Large Magellanic Cloud lies about 160,000 light-years from Earth, while the Small Magellanic Cloud is slightly farther, at roughly 200,000 light-years. Despite their names, these are not clouds at all. They are galaxies, irregular in shape, but teeming with star formation and complex structures. The Magellanic Clouds are gravitationally bound to the Milky Way, orbiting it on a long looping path. In fact, Observations suggest that the Magellanic Clouds are slowly being torn apart by the Milky Way's gravitational pull, their gas and stars gradually being absorbed into our galaxy's outer halo. There are others too, galaxies with names like Sculptor, Fornax, Sextines, and Draco. Most of these dwarf galaxies are so faint they can only be detected with powerful telescopes. They contain very little gas, and thus very few new stars. They are ancient, dim, and quiet, populated by old red stars that have been burning for billions of years. Yet they are essential to understanding how galaxies like the Milky Way formed. Computer simulations suggest that large galaxies grow by consuming smaller ones, a process called hierarchical merging. The dwarf galaxies we see today may be the last remnants of this process, survivors of a cosmic era when galaxies collided and merged far more frequently than they do now. The gravitational dynamics of the local group are both elegant and complex. Gravity is the force that binds these galaxies together, but it is not a simple attraction. Each galaxy exerts a gravitational pull on every other galaxy. Andromeda pulls on the Milky Way pulls on the Magellanic Clouds, Triangulum pulls on Andromeda. The result is a web of gravitational interactions, a cosmic ballet where every dancer influences the movement of the others. These forces are invisible, but their effects are profound. They shape the orbits of galaxies, trigger star formation, and determine the ultimate fate of the local group. The local group spans roughly 10 million light-years in diameter, a distance so vast it challenges comprehension. To put this in perspective, if the Milky Way were the size of a coin, the local group would stretch across a football field. Light itself, travelling at 186,000 miles per second, takes 10 million years to cross from one edge of the local group to the other. If a signal were sent from one side of the local group to the other today, it would not arrive until 10 million years from now. This is a neighbourhood where distance is not measured in miles but in epochs. Yet despite this immense scale, the local group is relatively isolated. Beyond its boundaries lies an expanse of nearly empty space, a void stretching for millions of light years before the next cluster of galaxies appears. The local group is a gravitational island, a bound collection of galaxies adrift in a sea of darkness. It is held together not by walls or boundaries, but by the mutual gravity of its members, a force strong enough to resist the expansion of the universe itself. While the universe expands, pulling distant galaxies away from each other, the galaxies within the local group remain bound, their fates intertwined. As we contemplate the local group, we begin to see the Milky Way not as the centre of everything, but as one participant in a much larger cosmic community. Our galaxy is not unique. It is one of many, shaped by the same forces, born from the same primordial gas clouds, evolving under the same physical laws. The stars that populate the Milky Way are no more special than the stars in Andromeda or Triangulum. The planets that orbit those stars may harbour life, just as Earth does. The future of the Milky Way is intimately connected to its neighbours, and in billions of years the distinctions between these galaxies will blur and fade. To stand at the edge of the local group is to witness gravity as a sculptor of the cosmos. It is not merely a force that pulls objects together. It is the architect of structure, the creator of galaxies, the force that binds the universe into coherent forms. Without gravity, galaxies would drift apart, stars would never form, and the universe would be a formless sea of gas and dust. But with gravity, we have the local group, a cosmic neighbourhood where galaxies cluster and interact, where stars are born from the debris of ancient collisions and where the future is written in the slow, inevitable dance of celestial bodies. The journey through the local group is not one of speed, but of contemplation. We cannot move through millions of light years in a single human lifetime. We can only imagine it, piece together the observations of telescopes, the calculations of physicists, the simulations of supercomputers. Yet in our minds, we can travel. We can stand at the edge of the Milky Way and look outward, seeing Andromeda glowing in the distance, watching. The Magellanic Clouds orbit like faithful companions, imagining the faint dwarf galaxies scattered across the void. We can see the local group not as a collection of separate objects, but as a single, interconnected system, a gravitational family bound together across the darkness. And as we prepare to journey even farther, to pull back our perspective once more and see the local group itself as just one small structure within a much larger cosmic web, we carry with us a humbling realization. The Milky Way, our home, is not the universe. It is not even a significant fraction of the universe. It is one galaxy among billions, a member of the local group, which itself is just one small cluster among countless others. The scale of the cosmos is not something we can hold in our hands or see with our eyes. It is something we must feel, something that expands our sense of place and reminds us that we are part of a universe far grander than any single world, any single star, or any single galaxy can contain. The local group is our neighborhood, but the universe, as we're about to see, is unimaginably vast. Beyond the local group, beyond the dance of nearby galaxies, we now venture into territories where distance becomes almost abstract. We leave behind the familiar neighbors of our Milky Way and enter a realm where thousands of galaxies move together like schools of luminous fish in an ocean of darkness. Here, gravity operates not on planets or stars, but on entire galactic empires. We are approaching the Virgo Supercluster, a vast congregation of galaxies that stretches across 110 million light-years of space. The Virgo Supercluster is not a single structure, but a collection of galaxy groups and clusters, all bound together by the invisible threads of gravity. At its heart lies the Virgo cluster itself, a dense concentration of more than 1,300 galaxies, their combined light creating a soft glow that astronomers can detect from Earth. Our own local group orbits on the outer edges of this supercluster, pulled gently toward the center by gravitational forces that operate across millions of light years. To comprehend this scale is to reimagine what we mean by neighborhood. The Virgo supercluster contains approximately 47,000 galaxies, each one home to billions or even hundreds of billions of stars. If the Milky Way were a single grain of sand, the Virgo supercluster would be a beach stretching beyond the horizon. Yet even this immense structure is merely a fragment of something far greater, a larger cosmic architecture that remained hidden from humanity until very recently. In 2014, astronomers made a discovery that fundamentally changed our understanding of our place in the universe. Using advanced mapping techniques that trace the motion of galaxies through space, they identified a supercluster so vast that it dwarfed even the Virgo supercluster. They named it Laniakea, a Hawaiian word meaning immense heaven. This colossal structure contains not just the Virgo supercluster, but more than 100,000 galaxies spanning 520 million light-years from edge to edge. Laniakea is not defined by proximity alone, but by motion. Galaxies within its boundaries are all flowing toward a common gravitational basin, like rivers converging toward the sea. Our Milky Way, along with all the galaxies in our local group, is part of this great cosmic current. We are not stationary observers of the universe. We are participants in a vast migration, moving at 600 kilometers per second toward a region of space that astronomers call the Great Attractor. The Great Attractor is one of the most mysterious features of our cosmic neighborhood. Located approximately 220 million light-years away, hidden behind the dense band of stars and dust in the Milky Way's disk, lies a gravitational anomaly so powerful it influences the motion of millions of galaxies. We cannot see the Great Attractor directly. The plane of our own galaxy obscures it, creating what astronomers call the zone of avoidance. Yet we know it exists because we can measure its effects. Galaxies across hundreds of millions of light-years are all being pulled in its direction. What is the Great Attractor? Is it a supermassive cluster of galaxies? A concentration of dark matter so dense it bends space itself? Or something else entirely, some feature of the universe we have not yet learned to recognize? Despite decades of observation, the Great Attractor remains partially veiled, a reminder that even with our most powerful telescopes, the universe still holds secrets. But the journey does not end there. Beyond the Great Attractor lies the Shapley Supercluster, an even larger concentration of galaxies that exerts its own gravitational influence across the cosmos. Some astronomers believe that the motion of Laniakea itself may be influenced by this more distant structure, creating flows within flows, currents within currents, like eddies in an infinite ocean of space. To understand these movements, we must visualize the universe not as a collection of isolated objects, but as a dynamic web of matter and motion. If we could step back far enough to see the distribution of galaxies across billions of light-years, we would witness something extraordinary. The universe is not uniform. It is structured like a cosmic spiderweb, with vast filaments of galaxies stretching across space, separated by enormous voids where almost nothing exists. These cosmic filaments are the largest structures in the universe. They can stretch for hundreds of millions of light-years, containing thousands upon thousands of galaxies arranged along invisible highways of dark matter. Between the filaments lie the cosmic voids, immense regions of near emptiness where galaxies are rare and darkness reigns. Some voids span 300 million light-years or more, containing so little matter that a journey across one would feel like crossing an infinite desert of absolute nothing. This web-like structure is not random. It is the signature of the universe's earliest moments, an echo of tiny quantum fluctuations that existed in the first fraction of a second after the Big Bang. As the universe expanded, these fluctuations grew, shaped by gravity, until they became the scaffolding upon which all galaxies, clusters, and superclusters were built. The filaments trace the distribution of dark matter, that invisible substance that makes up 85% of all matter in the universe. We cannot see dark matter directly, but we can see how it shapes the visible universe, how it pulls galaxies into patterns and streams, how it creates the architecture of cosmic space. Laniakea is one thread in this vast cosmic tapestry. Its 520 million light-year span contains not just galaxies, but the history of cosmic evolution itself. Within its boundaries, galaxies collide and merge, stars are born in brilliant nebulae, and black holes consume matter at the hearts of quasars. It is a realm where time and distance stretch beyond human comprehension, where a single light-year is but a step in a journey that spans 500 million light-years. To grasp the scale of Laniakea is to accept that our entire cosmic neighborhood Everything we have discussed so far, our planet, our solar system, our galaxy, our local group, all of it exists within a structure so large that light itself takes 520 million years to cross it. When that light began its journey, life on Earth consisted of primitive organisms in ancient seas. Dinosaurs had not yet evolved. Continents had not yet formed their modern shapes. The light that reaches us now from the far edge of Laniakea carries with it an image of the universe as it was before complex life existed on our world. Galaxy clusters within Laniakea do not drift aimlessly. They are organized into walls and sheets, massive concentrations of matter that define the boundaries between cosmic voids. The Great Wall, a colossal structure of galaxies stretching across 500 million light-years, is one such feature. Though it exists beyond Laniakea, it reminds us that superclusters themselves are not isolated islands. They are part of an even larger cosmic geography, a universal map written in the language of gravity and motion. As we observe these structures, we begin to understand that the universe operates on timescales that dwarf our own existence. The motions we measure now, the flows of galaxies toward the great attractor, the drift of Laniakea through space, these are processes that take billions of years to unfold. We are witnessing not just the structure of the universe, but its evolution, its slow transformation from the smooth, hot plasma of the early universe into the rich, complex web of matter we see today. The discovery of Laniakea also reveals something profound about the nature of cosmic identity. For centuries, humanity has asked, "Where are we?" We have answered with ever-expanding addresses: Earth, Solar System, Milky Way, Local Group. Now we add Laniakea to that list, a cosmic home so vast that it redefines what we mean by belonging. We are not just inhabitants of a planet or a galaxy. We are part of a supercluster, a community of 100,000 galaxies all flowing together through the darkness of space. Yet even Laniakea is not the final frontier. Beyond its borders lie other superclusters, each with their own structure, their own flows, their own gravitational centers. The Perseus-Pisces supercluster, the Coma supercluster, the Hercules supercluster, each one a vast congregation of galaxies separated by voids and connected by filaments. Together, these superclusters form a web that stretches across the entire observable universe, a tapestry of light and matter woven across billions of years. The cosmic web is not static, it is dynamic, evolving, expanding as the universe itself expands. Dark energy, the mysterious force that accelerates the universe's expansion, is slowly stretching the space between superclusters. In billions of years, the filaments will grow thinner, the voids will widen, and the cosmic web will become more diffuse. Distant superclusters will recede beyond the reach of light itself, disappearing from view as space expands faster than light can travel. The universe of the far future will be lonelier, darker, with each supercluster becoming an isolated island in an ever-expanding ocean of emptiness. But for now, in this epoch of cosmic history, we can still observe the web. We can trace the flows of galaxies, map the distribution of dark matter, and witness the grand architecture of the universe in all its glory. Laniakea is a reminder that we are part of something immense, something that connects us not just to our neighbouring galaxies, but to structures that span hundreds of millions of light years. As we contemplate this scale, our sense of self begins to shift. We are no longer just observers of distant objects. We are participants in a cosmic dance, moving through space as part of Laniakea, carried along by gravitational currents that have existed since the dawn of time. Our galaxy, our local group, our entire supercluster, all of it is in motion, flowing toward destinations we are only beginning to understand. The journey through Laniakea is not measured in years or even lifetimes. It is measured in epochs, in the slow turning of cosmic wheels that take billions of years to complete a single rotation. Yet here we are, conscious beings on a small blue world, capable of mapping these structures, of understanding our place within them, of grasping, however briefly, the true scale of the universe in which we live. To zoom out this far is to realize that the universe is not a collection of separate things, but a unified whole. Every galaxy is connected to every other galaxy through the invisible web of gravity and dark matter. Every star is part of a larger story, a narrative that began with the Big Bang and continues to unfold across billions of years. And we, impossibly small yet infinitely curious, have learned to read this story, to trace the filaments, to name the superclusters, to find our place in the immense heaven of Laniakea. We have travelled outward from our galaxy, through the local group, across the immensity of Laniakea. Now we arrive at the ultimate boundary, not a wall, but a horizon written in light itself. This is the edge of everything we can ever see, touch, or know. The observable universe, 93 billion light years. That is the diameter of our cosmic sphere, the bubble of space from which light has had time to reach us since the beginning of time itself. Within this incomprehensible expanse float approximately 2 trillion galaxies, each one a sprawling city of stars, many containing hundreds of billions of suns. 2 trillion islands of light, scattered across an ocean of darkness so vast that numbers begin to lose their meaning. To call this distance immense is to whisper in a hurricane. To comprehend it is nearly impossible. Yet we must try, for this is the canvas upon which our entire existence is painted. A canvas so large that our Milky Way, with all its grandeur and billions of stars, becomes less than a single brushstroke in an infinite masterpiece. The observable universe is not the entire universe. It is only what we can see. The distinction is profound. Light travels at a fixed speed, approximately 186,000 miles per second, the cosmic speed limit written into the fabric of reality itself. Nothing can move faster. This means that light from distant galaxies takes time to reach us, billions of years in some cases. When we look outward into space, we are simultaneously looking backward in time, seeing galaxies not as they are now, but as they were when their light began its journey toward Earth. The universe itself is approximately 13.8 billion years old, born in the explosive moment we call the Big Bang. One might assume, then, that we should be able to see objects 13.8 billion light-years away in all directions, creating an observable sphere 27.6 billion light-years across. But the universe does not remain still. It expands. Space itself stretches, carrying galaxies away from each other at speeds that, at great distances, exceed the speed of light. This is not a violation of physics. Galaxies are not moving through space faster than light. Space itself is growing between them. Because of this expansion, light from the most distant galaxies has been travelling for billions of years, while the space through which it travels has been stretching all the while. The galaxies that emitted that light have now moved much farther away than they were when the light began its journey. Accounting for this expansion, the most distant objects we can observe are now approximately 46.5 billion light-years away in every direction, creating our observable sphere of 93 billion light-years. Beyond this boundary lies a cosmic horizon, as absolute as any event horizon of a black hole. There exists a distance beyond which objects are receding from us so quickly that their light will never reach Earth, no matter how long we wait. The expansion of space carries them away faster than their light can travel toward us. We are surrounded by an invisible shell, beyond which lies a universe we can never see, never measure, never know. It is there, countless galaxies spinning in the darkness, but they exist forever beyond our reach, hidden behind the fundamental limits of physics and time. Within our observable bubble, the distribution of galaxies is both uniform and staggering. In every direction we point our telescopes, we find the same cosmic architecture, superclusters separated by vast voids, filaments of galaxies stretching like cosmic web strands across hundreds of millions of light years, walls of light separated by abysses of darkness. No matter where we look, the universe appears fundamentally the same, a principle called cosmic isotropy. There is no center, no preferred direction, no special location. The Milky Way sits not at the heart of creation, but adrift in an endless sea, one galaxy among 2 trillion others. Our local group is one gravitationally bound cluster among hundreds of thousands of others. Our Laniakea Supercluster is one superstructure among millions scattered throughout observable space. We're not special in location. We're not unique in composition. We are ordinary, cosmically speaking, profoundly humbling ordinary. Deep field observations have revealed this truth with startling clarity. When astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky, a region no larger than a grain of sand held at arm's length, they left the shutter open for days, collecting every photon that drifted into the lens. What emerged from that darkness was astonishing. Thousands of galaxies, each one a complete universe unto itself, filled the frame. Spirals, ellipticals, irregulars, galaxies colliding and merging, galaxies distorted by gravity, galaxies shining with the light of billions of stars. All of this in a patch of sky that appeared empty to the naked eye. This observation was repeated in different regions: the Hubble Deep Field, the Hubble Ultra Deep Field, the Hubble Extreme Deep Field. Each time the result was the same: thousands upon thousands of galaxies stretching back through time to within a few 100 million years of the Big Bang itself. The implication is staggering. Every point in the night sky, no matter how dark, is filled with galaxies. Billions of them. If we could see with eyes sensitive enough, the night sky would not be black at all. It would glow with the light of distant worlds, an unbroken tapestry of stars and galaxies overlapping in every direction, extending to the very edge of the observable universe. And within those 2 trillion galaxies, how many stars? Estimates suggest there are at least 200 billion trillion stars in the observable universe, a number so large it exceeds the grains of sand on all the beaches of Earth. And how many planets? Recent observations suggest that nearly every star hosts at least one planet, meaning there are likely more planets in the universe than there are stars. Hundreds of billions of trillions of worlds, each one unique, each one a distinct expression of cosmic chemistry and physics. How many of those worlds are like Earth? How many have liquid water, stable atmospheres, and the complex chemistry necessary for life? The statistics are beginning to emerge. Conservative estimates suggest that there could be as many as 40 billion Earth-sized planets in habitable zones around sun-like stars in the Milky Way alone. Multiply that by 2 trillion galaxies, and the number becomes incomprehensible. Even if only a tiny fraction of those worlds harbour life, The universe could be teeming with it. Microbial organisms clinging to frozen moons, intelligent civilizations gazing up at their own skies, wondering if they are alone. We may never know. The distances are too great, the speeds of expansion too fast. Even if a civilization existed in a galaxy 10 billion light-years away, we would see them not as they are now, but as they were 10 billion years ago, perhaps long extinct. And if they sent a message to us, travelling at the speed of light, it would take 10 billion years to arrive, by which time humanity itself may be gone. We are isolated not by walls, but by time at distance, separated from countless other worlds by gulfs so vast that communication may be impossible, even in principle. This realization is profoundly humbling. We live on a small rocky world, orbiting an unremarkable star in the outer regions of an ordinary spiral galaxy, drifting through a universe so vast that our entire existence occupies less space and time than a single atom in a cathedral. Every human who has ever lived, every civilization that has risen and fallen, every war, every discovery, every triumph and tragedy has occurred on a pale blue dot suspended in a sunbeam, invisible from even the nearest stars. Carl Sagan captured this perspective when he described Earth as seen from the edge of the solar system, a single pixel of light in the vastness. But even that perspective is insufficient. Zoom out further, beyond the solar system, beyond the Milky Way, beyond the local group and Laniakea, out to the scale of the observable universe, and Earth vanishes entirely. It becomes not just invisible, but irrelevant in terms of scale. Our planet, our sun, our entire galaxy are less than a whisper in a cosmic symphony. And yet, we are here. Against all odds, in a universe so vast and indifferent, matter organized itself into stars, planets, and eventually life. Atoms forged in the hearts of dying stars came together to form molecules, cells, organisms, consciousness. We are the universe becoming aware of itself, capable of looking outward and comprehending, however imperfectly, the immensity in which we exist. We are infinitesimal, yes, but we are also extraordinary. We are the cosmos reflecting on its own existence. What lies beyond the observable universe? We do not know. The universe may be infinite, stretching forever in all directions, filled with galaxies and stars beyond counting, forever hidden behind our cosmic horizon. Or it may be finite but unbounded, curved back upon itself like the surface of a sphere, so that travelling in one direction long enough would eventually bring you back to your starting point. It may even be one universe among many, a single bubble in an infinite froth of universes, each with its own laws of physics, its own constants, its own story. We may never answer these questions. The observable universe is all we have, all we will ever have. Beyond it lies mystery, infinite and eternal, and yet within our small bubble of perception, there is more to explore than we could ever hope to understand. 2 trillion galaxies, each one a universe of its own, filled with wonders and secrets waiting to be discovered. The Milky Way, our home, is just one thread in this vast cosmic tapestry. It is not special, not unique, not privileged. It is simply here, spinning quietly in the darkness, carrying with it a small blue world where beings have learned to ask questions about their place in the cosmos. And perhaps on countless other worlds scattered throughout those 2 trillion galaxies, other beings look up at their own night skies and wonder the same. We are part of something larger than we can comprehend. We are participants in a universe so grand, so ancient, so filled with mystery, that our minds can barely grasp its edges. And yet, we try. We build telescopes. We send probes into the darkness. We calculate and theorize and dream. We reach outward, knowing we will never touch the horizon, but driven by the unshakable human desire to understand. The observable universe is not just a measurement, it is a reminder that we are small, that we are brief, that we are cosmically insignificant in terms of scale. But it is also a reminder that we are here, now, in this moment, able to look out and see the grandeur of creation, able to comprehend, however incompletely, the true scale of existence. As we stand at the edge of the observable, peering into the vast darkness beyond, we carry with us a profound truth. We are not the center of the universe. We are not its purpose, but we are its witnesses. And in witnessing, in striving to understand, we become something more than dust. We become meaning in a cosmos that might otherwise have none. To speak of the Milky Way's place in the universe is to speak of distances so vast they seem to exist, beyond the reach of measurement. Yet, remarkably, we have found ways to map the cosmos, not with rulers or tape measures, but with light itself, with mathematics, with the patient accumulation of observations across generations. The story of how we measure the universe is not merely a technical achievement. It is one of humanity's greatest triumphs of imagination, a testament to our refusal to accept the darkness as unknowable. Every distance we have discussed, every light year and megaparsec, rests upon a foundation of ingenuity built layer by layer, stretching from the nearest stars to the edge of observable reality itself. Our journey into cosmic measurement begins close to home, with a method so elegant it was discovered not through advanced technology, but through simple geometry. Parallax, the apparent shift in position of an object when viewed from different locations, became humanity's first true ruler of the stars. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump against the distant background. This same principle, applied across the vastness of space, allows us to measure distances to nearby stars. As Earth orbits the Sun, we view the stars from slightly different positions 6 months apart. The nearest stars appear to shift ever so slightly against the backdrop of more distant stars, tracing tiny arcs across the sky. By measuring this shift, this parallax angle, astronomers can calculate distance with mathematical precision. The method works beautifully for stars within a few hundred light years, but beyond that, the angles become too small, the shifts too subtle even for our most sensitive instruments. Parallax gives us a cosmic foothold, a foundation upon which all other measurements rest. But to venture deeper into space, we need something more. We need objects whose true brightness we can know with certainty, beacons whose light tells us not just that they exist, but exactly how far away they are. These are the standard candles of astronomy, objects of known luminosity that serve as cosmic lighthouses. Among them, certain types of variable stars called Cepheids pulse with a rhythm directly tied to their intrinsic brightness. The longer the period of pulsation, the brighter the star truly is. By measuring how bright a Cepheid appears from Earth and comparing it to how bright it should be, we can calculate its distance. This relationship, discovered by Henrietta Swan Leavitt in the early 20th century, became the key that unlocked the scale of the universe beyond our galaxy. Cepheid variables carried us millions of light years into space, revealing that the fuzzy spiral nebulae once thought to be clouds within the Milky Way were in fact entire galaxies unto themselves, island universes separated by gulfs of emptiness. Yet even these reliable stars fade into invisibility at truly cosmic distances. To measure the space between galaxy clusters, to map the large-scale structure of the The universe itself, we needed something brighter still. We needed explosions visible across billions of light years. Enter the Typeia supernova, the most powerful standard candle in the astronomer's toolkit. These catastrophic events occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion star until it reaches a critical mass. At precisely 4 times the mass of our Sun, the Chandrasekhar limit, the white dwarf can no longer support itself against gravity. It collapses and rebounds in a thermonuclear explosion so brilliant it can briefly outshine an entire galaxy. The beauty of Typeia supernovae lies in their consistency. Because they always detonate at the same mass, they always reach approximately the same peak brightness. When we observe one of these cosmic detonations in a distant galaxy, we can compare its apparent brightness to its known intrinsic luminosity and calculate the distance with remarkable accuracy. These stellar explosions have become our measuring sticks across the deep universe, visible billions of light years away, allowing us to map the cosmos on scales that would have seemed impossible just decades ago. Yet distance alone does not tell the full story. The universe is not static. It is expanding, and within that expansion lies another method of measurement, one that transforms light itself into a cosmic ruler. As light travels through the expanding universe, space itself stretches, and the light stretches with it. Wavelengths become longer, shifting toward the red end of the spectrum. This redshift is not caused by motion through space, but by the expansion of space itself. The more distant a galaxy, the longer its light has travelled, the more space has expanded during that journey, and the greater its redshift. By measuring how much a galaxy's light has been stretched, we can determine not only how far away it is, but also how fast the universe was expanding when that light began its journey. This relationship, encoded in Hubble's law, ties redshift directly to distance. The universe becomes a vast echo chamber where light itself carries the signature of cosmic expansion, allowing us to measure distances to objects so remote they existed when the universe was young. Edwin Hubble's discovery that distant galaxies are receding from us, and that more distant galaxies recede faster, revolutionized our understanding of the cosmos. The universe was not eternal and unchanging, but dynamic, evolving, expanding from a moment of origin. Today, astronomers measure redshift with exquisite precision, analyzing the spectra of galaxies to determine their distances and velocities. This method has carried our measurements to the edge of the observable universe, to galaxies whose light has travelled more than 13 billion years to reach our telescopes, galaxies we see as they appeared when the universe itself was in its infancy. Yet to truly understand the scale and structure of the cosmos, we needed to see not just individual galaxies, but the entire history of the universe written across the sky. We needed to glimpse the universe as it was in its earliest moments, before stars existed, before galaxies formed, when space itself was filled with a hot, dense plasma of matter and radiation. That ancient light, stretched by cosmic expansion into microwave wavelengths, still fills the universe today. It is the cosmic microwave background radiation, the baby picture of the universe, a fossil record of creation itself. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the cosmic microwave background is the oldest light in existence, released approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely through space. This radiation bathes the entire universe in a faint glow with a temperature of just 2, 7 degrees above absolute zero. But it is not perfectly uniform. Tiny temperature fluctuations, variations of only a few millionths of a degree, mark regions that were slightly denser or slightly less dense in the early universe. These subtle ripples in the ancient light are the seeds from which all cosmic structure grew. The galaxies, clusters and superclusters we observe today formed from these primordial variations, gravity amplifying them over billions of years into the cosmic web we now inhabit. By mapping the cosmic microwave background with satellites like COBE, DubCMAP, and Planck, astronomers have measured the geometry, age, and composition of the universe with unprecedented precision. The patterns in this ancient light tell us that the universe is 8 billion years old, that it is geometrically flat, and that ordinary matter, the atoms that make up stars and planets and ourselves, comprises only about 5% of the universe's total content. The rest is dark matter and dark energy, invisible forces that shape cosmic evolution but reveal themselves only through their gravitational effects. The cosmic microwave background has become our Rosetta Stone for understanding cosmic scales, a map of the entire observable universe encoded in the oldest light that exists. Yet not all that fills the cosmos can be seen with optical telescopes. Between the stars throughout the spiral arms of galaxies drifts vast clouds of neutral hydrogen gas, invisible to our eyes, but detectable through radio waves. Hydrogen, the most abundant element in the universe, emits radiation at a characteristic wavelength of 21 centimeters when its electron flips between energy states. This radio signal penetrates dust clouds that block visible light, revealing the structure of galaxies from the inside out. Radio astronomy has mapped the spiral arms of the Milky Way, traced the rotation curves of distant galaxies, and revealed enormous hydrogen clouds stretching between galaxies like cosmic filaments. The 21-centimeter line has become one of astronomy's most powerful tools for understanding galactic structure and motion. By measuring the Doppler shift of this hydrogen emission, astronomers can determine how fast different parts of a galaxy are rotating. This is how we discovered one of the most profound mysteries in modern cosmology. When astronomers measured the rotation speeds of spiral galaxies, they found something impossible. Stars in the outer regions of galaxies were moving far too fast. According to the laws of gravity and the amount of visible matter present, these stars should have been flung into intergalactic space. Yet they remained bound to their galaxies, tracing stable orbits as if held by an invisible hand. The only explanation was that galaxies contain far more mass than we can see, an enormous amount of dark matter whose gravity holds galaxies together even though it emits no light. Radio observations of hydrogen revealed what optical telescopes could not. The universe is filled with invisible matter, 5 times more abundant than the ordinary matter from which stars and planets are made. This dark matter, though unseen, makes its presence known through gravity. And in the cosmos, gravity does more than pull objects together. It bends space itself. Einstein's general theory of relativity predicts that massive objects curve the fabric of space-time, and light travelling through that curved space follows a bent path. This phenomenon, gravitational lensing, has become both a tool for measuring cosmic distances and a window into the distribution of dark matter throughout the universe. When light from a distant galaxy passes near a massive foreground object, a galaxy cluster, for example, the cluster's gravity acts as a lens, bending and magnifying the background galaxy's light. Sometimes the effect is dramatic. creating multiple images of the same distant galaxy, arranged in arcs or rings around the foreground cluster. Other times the distortion is subtle, detectable only through careful analysis of galaxy shapes across large regions of sky. Gravitational lensing allows astronomers to weigh galaxy clusters, measuring the total mass present, both visible and dark. The results confirm what rotation curves suggested. Dark matter dominates the mass budget of the universe. But lensing does more than reveal invisible matter. It acts as a cosmic telescope, magnifying distant galaxies that would otherwise be too faint to observe. Some of the most distant galaxies ever detected have been found through gravitational lensing, their light amplified by foreground clusters into visibility. The universe itself becomes an instrument of observation, using gravity to show us objects at the very edge of observable space and time. All these methods, parallax, standard candles, redshift, the cosmic microwave background, radio mapping and gravitational lensing, work together like instruments in a vast orchestra, each contributing its unique voice to our understanding of cosmic scale. Yet to map the universe's large-scale structure, to understand how galaxies cluster and how those clusters organize into superclusters and filaments, requires something more. Comprehensive surveys that catalogue millions of galaxies across vast volumes of space. Modern astronomy has entered the era of big data. Telescopes like the Sloan Digital Sky Survey have mapped the positions and distances of millions of galaxies, creating three-dimensional maps of cosmic structure extending billions of light-years from Earth. These surveys reveal that galaxies are not randomly distributed through space. They form an intricate cosmic web, dense filaments and walls surrounding vast voids, a sponge-like structure shaped by dark matter and carved by cosmic expansion. The Laniakea Supercluster, our galactic home, emerge from these surveys as a coherent structure defined by the flow of galaxies through space. By measuring the peculiar velocity of galaxies, the motions not caused by cosmic expansion, but by local gravitational attraction, astronomers trace the gravitational watershed that defines Laniakea's boundaries. Each galaxy surveyed adds another point to the map, another piece of the cosmic puzzle. Together, these millions of measurements reveal patterns invisible on smaller scales. We see how structure has grown over cosmic time, how dark matter's gravity pulled galaxies together into clusters, how those clusters assembled into superclusters, and how the accelerating expansion of space driven by mysterious dark energy now works against gravity to prevent the formation of larger structures. The universe is a dynamic tapestry, and modern surveys are teaching us to read its patterns, to understand its history, and to glimpse its future. The methods we have developed to measure cosmic distances are not mere technical achievements. They represent something deeper, humanity's determination to comprehend its place in existence. Every distance we measure, every galaxy we map, pushes back the boundaries of the known and transforms the cosmos from an overwhelming darkness into a place we can navigate, at least in our minds. We cannot physically travel to distant galaxies or witness the cosmic microwave background directly as it appeared billions of years ago. Yet through light, through mathematics, through the patient accumulation of observations, we have learned to see across space and time, to measure distances that dwarf human comprehension, and to construct maps of a universe vast beyond imagination. The cosmic scales we now discuss with confidence, light-years and megaparsecs, redshifts and billions of years, rest upon this foundation of measurement. Every number carries within it the legacy of astronomers who looked up at the darkness and refused to accept ignorance, who built instruments and methods and theories to transform scattered points of light into a comprehensible cosmos. To know that the Milky Way is one galaxy among hundreds of billions, to understand that we reside within Laniakea, itself part of a vast cosmic web, is to participate in one of humanity's greatest intellectual journeys, a journey made possible not by travelling through space, but by learning to read the light that space delivers to us across the immeasurable distances of the universe. We have journeyed through scales so vast they challenge the very limits of comprehension. From our home galaxy stretching 100,000 light-years across, through the local group's millions of light-years, into the Laniakea Supercluster spanning 500 million light-years, and finally to the observable universe itself, a sphere containing 2 trillion galaxies extending 93 billion light-years from edge to edge. Now, as we pause in this cosmic meditation, we must ask ourselves, what does it mean to be human in a universe of such incomprehensible magnitude? The question is not new. For centuries we have grappled with our place in the cosmos, yet each discovery has pushed us further from the centre of creation. This progression, beginning with Copernicus, has become known as the Copernican principle, the realization that we occupy no special place in the vastness of space and time. Earth is not the centre of the solar system. The Sun is merely one star among hundreds of billions in the Milky Way. Our galaxy is not unique, but one of trillions scattered across the observable universe. Even our supercluster is but a thread in an incomprehensibly vast cosmic web. With each revelation, humanity has been displaced from centrality, pushed to the periphery of an ever-expanding stage. Some might find this realization disturbing. To be so small, so seemingly insignificant in the grand architecture of existence, could feel diminishing. If our entire planet is less than a mote of dust in the cosmic ocean, if our galaxy is merely one grain of sand on an infinite beach, then what meaning can our individual lives possibly hold? And yet, there is profound liberation in this smallness. When we truly comprehend our scale in relation to the universe, our perspective transforms. The worries that consume our days, the conflicts that divide us, the status and possessions we accumulate, all of these shrink to their proper proportion. Not into meaninglessness, but into clarity. We are not insignificant because we are small. We are remarkable precisely because we exist at all. Consider the improbability of your existence, the precise conditions required for matter to organize itself into living systems, the billions of years of stellar evolution needed to forge the elements in your body, the delicate balance of forces that allows planets to form and atmospheres to persist, the countless generations of life that preceded you, each surviving long enough to reproduce. You're not merely a person. You're the universe contemplating itself, 10 billion years of cosmic evolution compressed into consciousness. This realization brings us to one of humanity's most profound questions. Are we alone? The universe contains 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Many, perhaps most, of those stars host planets. The numbers become staggering. Conservative estimates suggest there may be more planets in the universe than grains of sand on all of Earth's beaches combined. Even if the conditions for life are extraordinarily rare, even if the emergence of consciousness is vanishingly unlikely, the sheer magnitude of opportunity suggests we may not be the only minds contemplating the cosmos. The Drake equation, formulated in 1961, attempts to estimate the number of communicating civilizations in our galaxy alone. While the variables remain uncertain, even modest assumptions lead to the conclusion that we should not be unique. Perhaps thousands or even millions of civilizations exist within the Milky Way. Multiply that across 2 trillion galaxies, and the cosmos may be teeming with consciousness, each civilization gazing up at their own night sky, wondering if they too are alone. And yet, we have heard nothing. The great silence of the cosmos remains unbroken. This paradox, known as the Fermi paradox, deepens the mystery. Where are they? Why do we detect no signals, no evidence of technology, no clear signs of intelligent manipulation of the cosmos? Perhaps life is far rarer than we imagine. Perhaps civilizations destroy themselves before reaching interstellar communication. Perhaps the distances are simply too vast, the timescales too long, for any 2 civilizations to overlap in their technological windows. Or perhaps we are truly alone. Perhaps consciousness is the universe's rarest and most precious phenomenon. Perhaps in all this vastness, only we have evolved the capacity to look outward and inward simultaneously, to measure the cosmos and to wonder at our own existence. This possibility, rather than being terrifying, should fill us with profound responsibility. If consciousness is rare, then we are the custodians of something infinitely valuable. We are matter that has organized itself to comprehend matter. We are the universe's way of knowing itself. Every human mind is a window through which the cosmos observes its own structure, contemplates its own origin, and ponders its own fate. No telescope has ever found a civilization among the stars. No message from distant worlds has reached our receivers. But every night, when we look up at the Milky Way stretching across the darkness, we are looking at the only home we have ever known. Earth, suspended in a sunbeam, orbiting an ordinary star in the outskirts of an unremarkable galaxy, remains the only place in the entire observable universe where we know with certainty that life exists. This makes our planet unimaginably precious. All of human history has unfolded on this small world. Every person you have ever heard of, every civilization that has risen and fallen, every work of art, every scientific discovery, every moment of joy and suffering, all of it has occurred here, on this pale blue dot suspended in the vastness. There is no other refuge, at least not yet, no other world we can escape to if we destroy this one, for now and for the foreseeable future. Earth is the only stage upon which the human drama unfolds. Understanding our cosmic scale changes everything about how we view human concerns. The borders that divide nations seem arbitrary when viewed from space. The conflicts that consume us appear petty when measured against cosmic time. The resources we fight over are revealed as shared treasures of a single fragile world. From the perspective of the universe, there is no us and them. There is only us, a single species on a single planet, temporarily granted the miraculous gift of consciousness. This perspective does not diminish human experience, it enriches it. Knowing that our lives are brief flickers in cosmic time makes each moment more precious, not less. Understanding that we are made of stardust, that the iron in our blood was forged in the hearts of dying stars, that we are literally children of the cosmos, this knowledge elevates existence from mundane to miraculous. The journey of cosmic discovery is far from complete. We have measured the observable universe, but we do not know if it is infinite beyond our observational horizon. We have catalogued 2 trillion galaxies, but we do not fully understand how they form or why they cluster in cosmic webs. We have detected dark matter through its gravitational effects, but we cannot identify what it is made of. We have discovered that the universe's expansion is accelerating, driven by mysterious dark energy, but we cannot explain why. Every answer we uncover reveals deeper questions. Every mystery we solve opens doors to greater mysteries. The universe is not a puzzle with a final solution, but an infinite unfolding of wonder. As our instruments improve, as our theories evolve, as our understanding deepens, we will continue to revise our cosmic map, to push back the boundaries of the known, to venture further into the great ocean of the unknown. And yet, perhaps the most profound aspect of our cosmic journey is not what we have discovered out there, but what we have learned about ourselves. We have learned that we are explorers by nature, driven to push beyond every horizon. We have learned that we are storytellers, weaving narratives to make sense of the cosmos. We have learned that we are scientists, using reason and observation to decode the universe's deepest secrets. Most of all, we have learned that we are part of something far greater than ourselves, participants in a cosmic story that began 13.8 billion years ago and will continue long after we are gone. Tonight, when you look up at the night sky, you will see it differently. That faint band of light stretching from horizon to horizon is not just a collection of distant stars. It is your home galaxy, the Milky Way, containing hundreds of billions of suns, perhaps trillions of planets, all rotating together in a grand cosmic dance. Those stars you see are your neighbours, fellow travellers through space and time, and beyond what you can see with your eyes lies layer upon layer of cosmic structure. The local group, our gravitational family, the Virgo Supercluster, our cosmic neighbourhood, Laniakea, the supercluster that defines our home region, and beyond that hundreds of thousands of other superclusters, each containing hundreds of thousands of galaxies, stretching away in every direction to the very edge of the observable universe. You're not separate from this vastness. You are part of it. The atoms in your body were forged in stellar furnaces. The elements that make you possible were scattered across space by ancient supernovae. You are not in the universe. You are of the universe. You are a way for the cosmos to know itself. This knowledge, this perspective, is the gift of cosmic scale. It offers humility without despair, wonder without confusion. It reminds us that while we may be small in physical scale, we are vast in our capacity for understanding. We are the universe's consciousness, its eyes and ears and minds. Through us, the cosmos has developed the ability to observe itself, to measure its own dimensions, to ponder its own existence. In this vast and ancient universe, on a small planet orbiting an ordinary star, consciousness has emerged. It has learned to ask questions, to seek answers, to build instruments that can peer billions of light years into space and billions of years into the past. It has learned to map its cosmic address, to understand its place in the grand architecture of existence. And now, having measured the true scale of the Milky Way in the universe, we carry this knowledge forward, not as a burden, but as an invitation to look up with wonder, to recognize our connection to all that is, to protect the fragile world that gave us birth, to continue the journey of discovery that defines us as a species. The universe is vast beyond comprehension, ancient beyond measure, and filled with mysteries that will occupy countless generations of explorers. But it is also your home, and tonight, as you drift towards sleep, you can rest knowing that you are part of something magnificent, a cosmic story still being written, a universe still revealing itself, one discovery at a time. We have travelled far tonight, farther than any spacecraft could carry us. From the familiarity of Earth, we ventured outward through the spiral arms of our Milky Way, past countless stars that burn in the darkness like ancient lanterns. We traced the boundaries of our galactic home, a luminous disk 100,000 light-years across spinning slowly through the void. We discovered that our galaxy, vast beyond human comprehension, is merely one island in an archipelago of galaxies stretching across cosmic oceans we can barely fathom. We zoomed out further still, beyond the local group with its gravitational dance of galaxies, beyond the Laniakea Supercluster, where hundreds of thousands of galaxies flow like rivers toward a common center. We reached the edge of the observable universe itself, that sphere 93 billion light-years across, where light from the earliest moments of creation is only now reaching our telescopes. And there, at that unfathomable scale, we saw the Milky Way not as a galaxy, but as a point of light, a single grain of sand on an infinite cosmic shore. This journey has not been measured in miles alone, but in moments of reflection. Every scale we crossed from Earth to Supercluster reminds us that we are simultaneously insignificant and extraordinary. The Milky Way is our home, the birthplace of everything we know, everyone we have ever loved, every story ever told. Yet it is also just one note in a symphony so vast that most of it will never reach our ears. This paradox does not diminish us, it elevates us. To comprehend even a fraction of this scale is to touch something profound. As you prepare to drift into sleep or simply rest in quiet contemplation, carry this perspective with you. Let the enormity of the cosmos be not a source of anxiety, but of peace. We are small, yes, but we are also witnesses to infinity. We are stardust that has learned to wonder, atoms that have opened their eyes and glimpsed the architecture of existence itself. In the grand scale of the universe, our worries, our fears, our daily struggles are fleeting whispers. But our capacity for awe, our ability to look up and ask questions about our place among the stars, that is eternal. The Milky Way continues its slow rotation through the night sky, indifferent to our observations, yet intimately connected to our existence. Every atom in your body was forged in the heart of ancient stars, scattered across space, and eventually gathered into the world beneath your feet. You're not separate from the cosmos. You are the cosmos experiencing itself, a brief but brilliant expression of the universe's endless creativity. Before you close your eyes tonight, take a moment to appreciate the journey we have shared. From the familiar blue marble of Earth to the incomprehensible edges of observable space, we have explored not just distance, but meaning. We have discovered that wonder does not require answers. It requires only the willingness to look, to question, and to marvel. If this journey has resonated with you, consider leaving a like on this video and share in the comments where in the world, or perhaps where in the Milky Way, you are listening from tonight. Subscribe to join us on future explorations through the cosmos and the profound questions it inspires. Now, let the universe hold you gently. Let the knowledge of your cosmic home settle into your thoughts like starlight filtering through ancient clouds. May your sleep be deep, your dreams expansive, and your rest as peaceful as the silent spaces between the stars. Good night, fellow traveler. The cosmos awaits your return.